Hello and welcome to this Try Get Maths video on Hooke's law looking at elastic energy. So if we want to consider what we mean by work done to extend a string, we can think about taking a string and extending it by a different amount and thinking about what the tension in the string is at any point. Now we know that work done is force times distance. So looking at this situation here, if I want to know at this point here, what is the work done by stretching the string out to this point, then that will be the force times the distance. So the force is lambda x over L, any point here, multiplied by the distance. So we're going to multiply it by x. And that's this area here, force times distance. That area is going to give me that amount. So I need the area of the triangle, so I'm going to divide that by 2. So the tension is equal to lambda x over L. The work done is lambda x over L multiplied by x and then divided by 2 because we're looking at the triangle here. So the energy stored in a string is the same as the work done to extend it, and that's lambda x squared over 2L. Sometimes you say a half lambda x squared over L. So that's where you take the 2. And that's also called the elastic potential energy that's needed to return the string to its natural length. So let's have a look at how we use these formulae. We've got an elastic string, length 1.6, and a modulus of elasticity 5. Find the work done when it's stretched from its natural length to a length of 2. So just drawing a little diagram here. Here's the string. Natural length is 1.6. It's stretched out to a length of 2. So the extension is 0.4. So writing those quantities down so that we're clear, the natural length is 1.6, the extension is 0.4, and we're told that lambda is equal to 5. So we're going to use this formula here, that the work done, WD, is equal to lambda, which is 5, x squared, 0.4 squared, over 2 times the natural length, 2 times 1.6. And when you work that out, you get 0.25. So we're looking at work done. The unit is going to be 2.5 joules. Next question. We have a light elastic spring of natural length 0.4, modulus of elasticity 6, and it's compressed. Find the potential energy stored in the spring. Again, just a little diagram so that you are clear on what is happening. Here's the spring. Its natural length was 0.4. It's compressed to a length of 0.1. So that means the compression is 0.3. Obviously, my diagram not to scale here. What else do we know? We know that lambda is 6 and the natural length is 0.4. So the elastic potential energy in the spring is going to be lambda, which is 6, x squared, which is 0.3 squared, over 2 times 0.4. And when we work that out, that's 0.675 joules. Now, it's called elastic potential energy because the spring now has the capacity to do some work. If you imagine that spring was pushed in like that, if you let it go, it would be able to push something else back again. So that's a way of thinking about the elastic potential energy. Moving on to the next question. We've got a spring with a natural length of 0.5 and a modulus of elasticity 12. Find the work done when it's compressed from a length of 0.4 to a length of 0.2. So what we've got here is our spring and it was at a length of 0.4, so its natural length is 0.5. It was at 0.4, and we've moved it in to 0.2. So that's the situation. We've moved it from here to here. And what the question is, what's the work done? So we need to look at the work done in compressing the spring to the two different places and find the difference between that. So if we look at the first position here, this would be this first position A. What's the energy stored in the spring at A? So at A, the extension or compression is 0.1. The modulus of elasticity is 12, and the natural length of the spring is 0.5. So the energy stored at A is lambda, which is 12, multiplied by x squared, 0.1 squared, over 2 times the natural length. So that's the energy stored at A. At B, the extension this time is 0.3. Lambda is 12, L is 0.5. So the elastic potential energy at B is going to be 12 multiplied by 0.3 squared over 2 times 0.5. So working both of these out, we get the work done is going to be the change in the energy from there. So the work done is going to be whatever it had at B, take away whatever it was at A, because it's got more energy here. So that's going to be 1.08 minus 0.12. And that gives me an answer of 0.96 joules. Notice that you must work with the compression at any given point. You cannot say that you've compressed it a complete distance of 0.2 and use that as your x, because compressing it a distance of 0.2, say from 0.5 to 0.3, is not as hard work as going from 0.3 to 0.1, for instance. So it depends whereabouts on the spring you are when you compress it. So you must work at what's the energy at one position, what's the energy at another, and find the difference between those two amounts. The last question has a light elastic string, natural length 1.7, attached to a fixed point A, and then we've got something hanging down off the string in equilibrium. So we've got this going on like this. Let's draw a diagram. We've got a tension in the string. We've got 0.3, no, we've actually got 3G acting down. The natural length is 1.7. The modulus of elasticity is 15. And we don't know what the extension is. So we need to work these values out in order to find the energy in the spring. It's in equilibrium. So that means the tension in the string must be 3G. But we also know that the tension in the string is lambda x over L. So using this equation here, we've got that the tension in the string is also equal to 15 times x, which we want to find out, over the natural length, which is 1.7. So equating these two, we get that 3G is 15x over 1.7, and that leads me to getting x equals 3.332. Now we want to know what's the elastic potential energy. Elastic potential energy, that's going to be lambda, which is 15, x squared, I've just found that, 3.332, but on your calculator, use the full value from here, divided by 2, multiplied by the natural length of the string, which is 1.7, and that gives me 48.9804 joules. But in mechanics questions, when you've used G, you must give your answer to 3 significant figures. So I would give this answer as 49.0 joules to 3 significant figures. So the key equation that you need to remember for elastic energy is that the elastic energy stored in a string is lambda x squared over 2 times the natural length.